Principle of linear impulses and momentum. The principle of impulse and momentum describe how an object's linear and angular momentum change with applied forces and moments. This is known as the principle of linear impulse and momentum. It applies to both particle motion and rigid body motion. It means that in every object, when there is force, the momentum and the impulse will be changed. This is the difference between impulse and momentum. Momentum is mass in motion, and any moving object can have momentum. This means that when you put force on an object, then the object moves. There is a momentum. An object's change in momentum is equals to its impulse. This means that when you put force to a moving object, then the momentum of an object move or change. There is impulse. Impulse is a quantity of force times the time interval. It is the change of direction and time. Impulse is not equal to momentum itself, rather it's the increase or decrease of an object's momentum. This is basically the change of momentum. We're not forgetting the momentum. P is equals to mv, where P is the momentum, m is the mass or force, v is the velocity. This is the speed and direction given. This is the formula in getting the impulse. Triangle P is equals to F triangle T, where triangle P is equals to the change in momentum, F is equals to the force, and triangle T is equals to the time. Let's have a sample problem with the topic of linear impulses and momentum. This sample problem, number 1, is based on a statement by Timothy Treadwell. Now, the birds I live with average, the males 8 to 1200 pounds. They're the largest bird in the world. They've been clocked at 41 miles per hour, and they've run 100-meter dash in 5.85 seconds, which a human steroid doesn't even approach. Question letter A. Compute the speed of grizzly bear using Mr. Treadwell's 100-meter statement. Letter B. Compute the momentum of grizzly bear using the speed you calculated in part A and the average mass stated by Mr. Treadwell. Letter C. How fast would a 250-pound man to have to run to have the same momentum you could calculate in part B? For question letter A, we need to find the speed of the grizzly bear using Mr. Treadwell's 100-meter statement. First, we need to find what is given. The givens are the distance and time. The formula in getting the speed is V is equals to S over T. S is equals to distance and T is equals to time. V is equals to 100 meters because we have given 100 meters using the 100-meter statement over 5.85. V is equals to 7 meters per second. This is the speed of the grizzly bear. For question letter B, we need to find the momentum of a grizzly bear using the speed we calculated in the part A. We are given mass, which is 450 kilograms, the speed, which is 17 meters per second, and the P, which is unknown. This is the momentum. The formula for momentum is m over v, which is P is equals to mass times velocity or speed. P is equals to 450 kilograms multiplied by the 17 meter per second. Then P is equals to 17 kilograms per meter per second. Then that's the momentum of the grizzly bear. For question letter C, how fast would the 250-pound man have to run to have the same momentum you calculated in part B? First, you need to find the given. P bear is equal to 17 meter per second. This is the momentum of the bear. M man, this is the mass of a man, is equals to 1/4 mass of the bear. Then 4V man, which is the speed of a man, is equals to speed of the bear. This means that momentum is the product of mass and velocity, which makes the two quantities inversely proportional. Mass goes down when we replace the 1,000-pound grizzly bear with a 250-pound man. That's why it is for 1/4 M bear is equals to 1 M man. To keep the momentum constant, the man will have to run faster. Faster by the amount that is inversely proportional to the decrease in weight. Since our hypothetical mass has 1/4 the mass of grizzly, he needs to run 4 times faster to have the same momentum. Our formula will be P is equals to mv, which is momentum is equals to mass times velocity or speed. P is equals to 1/4 m because 1/4 of the mass of the bear is equals to the mass of the man, multiplied by the 4v because for every 4 V man there is 1 bear. V man is equals to 4V bear to get the momentum. V man is equals to 17 meter per second because 17 meter per second is our original momentum. Multiplied by 4, you can get V man is equals to 68 meter per second. And that's the momentum of the man. Question number 2 for the topic of linear impulses and momentum. A 10-gram ball falls freely from a height, hits the floor at 15 meter per second, then reflected upward at 10 meter per second. Determine the impulse solution. We have given mass is equals to 10 grams or 0.01 kilograms, initial velocity of negative 15 meter per second. It is negative because it is falls freely. Then a final velocity of 10 meters per second because it is reflected upward. Because for velocity, if it is downward, it is negative. For upward, it is positive. Then we have unknown impulse. The formula in getting the impulse is F triangle T. But in this case, we use I is equals to mv1 minus mv0, which is mass times initial velocity minus final velocity. Impulse is equals to 0.01, which is the mass, multiplied by 10 minus negative 15. I is equals to 0.01 times 10 plus 15. We get 0.025 kilograms meter per second. That's the new momentum of the ball. Okay, for our next topic, we will talk about the conservation of momentum in a system particle. What happens when a group of particles are all interacting? Qualitatively speaking, each exerts equal and opposite impulses on the other, which means that there are many forces acting to one object that is moving. And though the individual momentum of any given particle might change, the total momentum of the system remains constant. It means that whenever you applied force to one moving object, the momentum of the object will remain the same. This phenomenon of momentum constancy describes the conservation of linear momentum in a nutshell. In this section, we shall prove the existence of the conservation of energy by using what we already know about momentum in system of particles. The formula in getting the conservation of momentum in a system particle. Just as we first define kinetic energy for a single particle, and then examine the energy of a system, so shall we know to term the linear momentum of a system of particles. Suppose we have a system n particles. This n particle is the object with masses m1, m2, and so on and so forth. Assuming no mass enters or leaves the system, this means that the mass is constantly in the moving object. We define the total momentum of the system as the vector sum of the individual momentum of the particles. This means that all the momentum acting on the n particles will be equal to the total momentum of the system, which means that the total momentum of the system is equals to the m1 v1, which is the mass 1 velocity 1, plus the mass 2 velocity 2, plus the mass 3 velocity 3, and so on and so forth. Let's have an example for conservation of momentum. Question number 1. Consider a 42,000 kilograms train car traveling at 10 meters per second towards another train car. After two cars collide, they couple together and move along at 6 meters per second. What is the mass of the second train car? I'm sorry because the image is not readable. I'll just explain it later. Here's the solution for problem number 1. In a closed system, momentum is conserved. This means the total momentum of the system remains unchanged. Before the collision, the momentum was the sum of the momentums of both train cars. Here's the solution. Momentum blue is equals to mv, which is mass times velocity. 42,000 multiplied by 10 meters per second. Then we get 420,000 kilograms meter per second. The second car is the tanker car. It's just the same with the first car, mass times velocity, which is mass times 0 because it is not moving. Add the two together to get the total momentum, which is 420,000 plus 0. We get 420,000 kilograms meter per second. That's the total momentum. After the collision, the two cars couple together into one mass. This new mass is mass blue plus mass tanker is equals to 42,000 kilograms plus mass tanker. The velocity of the new pair of car is traveling 6 meters per second. Because momentum is conserved, we know the total momentum of the cars after the collision is equal to the momentum prior to the collision. Total momentum is equals to 420,000 kilograms meter per second. The total momentum formula is mass times velocity. The total momentum is equals to 42 kilograms plus the mass tanker times the new velocity, which is 6 meter per second. 420 kilograms is equals to 42 kilograms plus the mass tanker, which is the unknown, multiplied by the new velocity. Divide both sides by 6 to isolate the mass tanker. 70 kilograms equals to 42 kilograms plus mass tanker. Subtract 42,000 kilograms from both sides. So the new mass of the tanker is 28 kilograms. The mass of the second car is equals to 28 kilograms. Remember, the momentum of a system is conserved. The momentum of the individual masses may change, but the net momentum of the system does not change. Okay, let's have another example. Two cars are stationary at the beginning. If the car having 10 kg mass starts to move to the east with a velocity of 5 meters per second, find the velocity of the car having mass of 4 kg with respect to the ground. First, we will write down the given. Mass 1 is equals to 10 kilograms. Mass 2 is equals to 4 kilograms. Velocity 1 is unknown. Velocity 2 is 5 meter per second. So here's the solution for question number 2. We will use the conservation of momentum formula, which is the final momentum is equals to momentum number 1 plus momentum number 2. The initial momentum will be equal to 0 because it is not moving. final momentum is equals to 4 kilograms v1, which is the formula for momentum is mass times velocity, plus 10 kilograms times 5 meter per second. You can see Pi is equals to Pf because it's not moving. 0 is equals to 4 kilograms v1 plus 50 kilograms meter per second. Transpose 4 kilograms v1 to the left side, then divide both sides by 4 kilograms. You will get v1 is equals to 12.5 meter per second. If you want to find the velocity of the small car with respect to big car, you should benefit from relative motion and do your calculation according to the vector properties. In other words, you must consider the direction of the velocities. Okay, for our next topic, we will talk about angular momentum. Angular momentum, it is a property characterizing the rotary inertia of an object or system of objects in motion about an axis that may or may not pass through the object or system. For example, the Earth has orbital angular momentum by reason of its annual revolution about the Sun, and spin angular momentum because of its daily rotation about its axis. Angular momentum is a vector quantity, which requires the specification of both magnitude and direction for its complete description. The magnitude of the angular momentum of an orbiting object is equal to its linear momentum, product of its mass and linear velocity, times the perpendicular distance r, which is sometimes it is the radius from the center of rotation to a line drawn in the direction of its instantaneous motion and passing through the object's center of gravity, or simply MVR. For spinning object, on the other hand, the angular momentum must be considered as the summation of the quantity MVR for all the particles composing the object. Angular momentum may be formulated equivalently as the product of I, the moment of inertia, and W, the angular velocity of a rotating body or system, or simply I times W. The direction of an angular momentum vector is that of the axis of rotation of the given object is designated as positive in the direction, and the right hand screw would advance if turned. Here are the basic formulas in getting the angular momentum. The first formula is L is equals to MVR, where L is equals to the angular momentum, M is equals to the mass, V is equals to the velocity, and R is equals to the radius. The second one is L is equals to I times W. I is equals to the inertia, and W is equals to the angular velocity. Okay, let's have an example for angular momentum. Example number 1. A 236.8 kilogram particle rotates at a constant angular speed of 16 rad per second. What is the angular speed if the radius of the circle is 66.87 cm? First, we will write down the given, which is m is equals to 236.8. This is the mass. W is equals to 16 rad per second, which is the angular speed, and r is equals to 66.87 cm. This is the radius, and lastly L, which is unknown, and this is the angular momentum. To solve this problem, first we will get the moment of inertia because we will use the formula L is equals to I times W because we were given a angular speed. To get the moment of inertia, we will multiply mass multiplied by r to the second power. That's why 236.8 multiplied by 0.667 meters squared. 0.667 meters squared was originally 66.87 cm. 236.8 multiplied by 0.667 meters squared is equals to 105.35 kilogram meters squared. And to get the angular momentum, we will multiply the moment of inertia multiplied by angular speed. 105.35 multiplied by 16 is equals to 1685.6 kilogram meter squared per second. Okay, let's have another example for angular momentum. What is the angular momentum around the catcher of a baseball thrown at 40 meter per second? The weight of the baseball is 145 kilograms, and on a wild pitch, the catcher has extended his arm 1.25 meters from his center of rotation. First, we'll write down the given, which is m is equals to 145 kilograms, v is equals to 40 meter per second, which is the velocity, and r is equals to 1.25 meters, and L is the angular momentum, which is unknown. In this case, we will use the another formula, which is L is equals to mRV. L is equals to 145 kilograms multiplied by 1.25 meters multiplied by 40 meter per second is equals to 7.25 kilogram meter squared per second. Okay, for this topic we will talk about relation between momentum of force and angular momentum. We often deal with an object moving from one place to another. You might see problems that involve situations such as ball being dropped from the roof or a book sliding down a ramp. There are examples of translational motion, meaning an object travels from one point to another. However, this is not the only type of motion an object can experience. There is another type of motion we see in physics. It is the rotational motion. It happens when an object spins around an axis. You can see rotational motion in objects. For example, a bicycle wheel spinning around its center, or the Earth's rotation around its poles. When we compare translational and rotational motion, we find that the two have similar physics quantities. For example, translational motion has linear velocity, force, and linear momentum. Correspondingly, rotational motion has angular velocity, torque, and angular momentum. In this lesson, we're going to focus on angular momentum and its relation to moment of force. Now that we know that angular momentum is, let's start looking at how torque affects it. As we saw in the beginning of this lesson, torque is the equivalent of force for the rotational motion. In fact, torque can be described as twisting force that causes rotation. This is a little misleading, however, as torque isn't exactly a force. Torque, or tau, is a force multiplied by radius multiplied by the sine of the angle theta at which the force is applied. This is the formula in getting the torque. T is for tau is equals to force times r, which is the radius, times sine theta. So this is how torque being related to angular momentum. We need to think about how objects in rotational motion can get moving in the first place. Have you ever thought about what gets a wind turbine spinning? You know it's the wind, but what exactly is the wind doing? It's pushing on the wind turbine's blade, applying a force to the blade at some angle and radius from the turbine's axis of rotation. In other words, the wind is applying a torque to the wind turbine. Torque is what gets rotatable objects spinning when they're standing still. Also, if object in the direction it's spinning, it increases its angular velocity. If it's applied in the opposite direction the object is spinning, it decreases its angular velocity. So torque is directly affecting the angular velocity of a spinning object. Remember that our angular momentum equation tells us that angular momentum is moment of inertia multiplied by angular velocity. Since torque can change angular velocity and the amount of angular momentum of object has depends on its angular velocity, it makes sense that torque can change angular momentum. In short, torque is the rotational equivalent of force and angular momentum is the rotational equivalent of translational momentum. This can be extended to rotational motion as follows. Tau is equals to dl over dt, which is torque is the rate of change of angular momentum. For the next topic, we will talk about principles of angular momentum and impulse. L is equals to IW. L is angular momentum, I is rotational inertia, and W is angular velocity. Angular momentum of a spinning object without linear momentum is proportional to rotational inertia and angular velocity. L is equals to mvr. L is angular momentum, m is mass, v is linear velocity, and r, that subscript and end subscript in perpendicular radius from a chosen axis to the mass line of motion. Angular momentum of an object with linear momentum is proportional to mass. Linear velocity, perpendicular radius from an axis to the line of the object's motion. Triangle L is equals to tau triangle T. Triangle L is change of angular momentum, tau is net torque, and triangle T is time interval. Change in angular momentum is proportional to average net torque and the time interval the torque is applied. Okay, let's have an example for this topic. Calculate the angular momentum of a phonograph record LP rotating at 33 1/3 revolution per minute. An LP has radius of 15 cm and a mass of 150 grams. A typical phonograph can accelerate an LP from rest to its final speed in 0.35 seconds. What average torque would be exerted on the LP? First, the angular momentum of a rotating body is L is equals to I times omega. This means that angular momentum is equals to the moment of inertia multiplied by omega. An LP is a solid disk. Consulting a table of moments of inertia, we find that I is equals to 1/2 mr squared. The angular velocity must be converted to rad per second. To convert that, this is the formula. Omega is equals to 100 over 3 revolution per minute multiplied by 2 pi rad per revolution multiplied by 1 minute over 60 seconds. This will be equal to 3.4907 rad per second. Thus, we find the angular momentum of the LP to be L is equals to I times omega. This is equal to 1/2 mr squared times omega. Then substitute it. 1/2 multiplied by 0.15 kilograms multiplied by 0.15 meters squared multiplied by 3.4907 rad per seconds. This will be 5.8905 times 10 raised to negative 3 kilogram meter squared per second. Then we will get the torque. Torque is equal to the change in angular momentum with time. So it means the angular momentum will change with respect to time. This is the formula in getting the torque. Tau, which means this is the symbol for torque. Triangle L, which means change in angular momentum, over triangle T, which is change in time, is equals to initial momentum minus the final momentum over triangle T. Substitute it, we will get 5.8905 times 10 to the third power kilogram meter squared per seconds minus 0 over 0.35 seconds is equals to 1.68 times 10 raised to negative 2 Newton per meter, and that's the okay. For our second example, a 22-gram bag crawls from the center to the outside edge of a 150-gram disc of radius of 50 cm. The disc was rotating at 11 rad per second. What will be its final angular velocity? Treat the bag as a point of mass. There will be a change in rotation of the bag's move, so we use the conservation of angular momentum. This is final momentum is equals to initial momentum. Assuming that the bag doesn't slip, then it rotates at the same velocity as the disc. The bag rotates in a circle. The angular momentum of an object moving in a circle is r squared m omega, where r is the radius of rotation. The center of the disc r is equals to 0. Initially, at the final position, the edge of the disc is r is equals to r. The disc is rotating and thus an angular momentum by I omega. Consulting a table of moments of inertia, we find I is equals to 1/2 mr squared. Equation number 1, r squared m omega f plus 1/2 mr squared omega f is equals to 0 squared, which is 0 is equals to r. 0 squared multiplied by m initial omega plus 1/2 mr squared initial omega. Dividing through by 1/2 r squared and solving for final omega, we find Final omega is equals to m initial omega over 2m plus m. This is equals to 0.15 multiplied by 11 rad per seconds divided by 2 multiplied by 0.022 plus 0.150. This will be equal to 8.51 rad per second. Okay, for second to the last topic, we will talk about the steady flow of a fluid stream. First, we will define streamline flow. In case of fluids is referred to as the type of flow where the fluids flow in separate layers without mixing or disruption occurring in between the layers at a particular point. The velocity of each fluid particle flowing will remain constant with time in streamline flow. Steady flow. The flow is steady when the velocity of every particle within the fluid is constant in time. However, this statement does not mean that the velocity of fluid particles will not vary at a different point in space. The velocity of a fluid particle can change as the fluid moves from one particular point to another. This means that at a different point, the particle can have different velocity. Steady flow signifies that each particle passing through the second point will behave the same as the previous fluid particle that has initially crossed the point. This steady flow means that when a particle moves in point to another point, it will be constant. Therefore, under steady flow condition, the fluid particles that has initially crossed that point. Therefore, under steady flow condition, the fluid particles will follow a smooth path that will not cross each other. Hence, streamline is the path taken by fluid particles under the steady flow condition. In case of a streamline flow, the tangent drawn at any point of the curve will be in direction of the velocity of the fluid at that point. Here's the diagram for steady flow. Below is the diagram represents a curve with tangents at different points. It describes how the particles present within a fluid moves with respect to time. As you can see, the flow is constant from one point to another. The diagram acts as a permanent map to describe how the fluid flows during streamlines condition. Thus, no two streamlines can intermix or each other, or it means the flow will not intersect with each other. Under steady flow, the map of the movement of fluid is stationary with respect to time. Hence, the continuum of lines will form if we try to describe the streamline flow of every particle. This means that the flow of the particle will be at the same direction. Here is another representation of the steady flow line. Consider three parts P, R, Q in planes that are present in the perpendicular direction to the fluid. Reverse of the diagram. Look, as you can see, it has the same direction but different in size. We will be able to determine the boundaries that selected points in the plane by the same set of streamlines. Hence, the particles of fluid passing through the surfaces at the 3 point P, R, and Q will be the same. Now consider the area at the 3 points R sub P, A sub R, and A sub Q. Consider the speed of the fluid particle has. Here's how to calculate a steady flow of a fluid stream. The mass of the fluid M sub P crossing at the area A sub P at small time interval t will be P sub P, A sub P, and V sub P multiplied by t. Similarly, the mass of fluid M sub R and M sub Q will be P sub R, A sub R, and V sub R and T, passing at A sub P and A sub Q respectively at small interval of time at. In all the three cases, the mass of fluid flowing will be equal. Therefore, we can write the equation as P sub P, A sub P, V sub P times T is equals to P sub R, A sub R, V sub R times T is equals to P sub Q, A sub Q, V sub Q times T. If we consider the fluid as incompressible in nature, then P sub P is equals to P sub R is equals to P sub Q. So the above equation can be rewritten as A sub P V sub P is equals to A sub R V sub R is equals to V sub Q after elimination of P. The above equation is the equation of continuity. The equation also represents conservation of mass in case of the flow of the incompressible liquids. General equation of continuity. A sub V is equals to constant, where A sub V is the flow rate of the liquid or volume flux of the liquid. The flow rate in the streamline flow remain constant throughout the flow of the liquid to the pipe. Here is another equation we use in getting steady flow of a fluid stream. The simplified form of Bernoulli's equation can be summarized in the following memorable equation. This is static pressure plus dynamic pressure is equals to total pressure. Every point in a steadily flowing fluid, regardless of the fluid speed at the point, has its own unique static pressure and dynamic pressure, which is P and Q. Here are other equations to use when getting steady flow. Discharge, or also called as flow rate. The amount of fluid passing a section of a stream in unit time is called the discharge. If V is the mean velocity and A is the cross-sectional area, the discharge Q is defined by Q is equals to AV, which is known as volume flow rate. Discharge is also expressed as mass flow rate and weight flow rate. This is the formula. Volume flow rate is Q is equals to AV. Mass flow rate is M is equals to PQ, M is equals to PQ. Weight flow rate is equals to W is equals to YQ, where Q is equals to discharge in cubic meter per second or feet cube per second. A is equals to cross-sectional area of flow in meter squared or feet squared. V is equals to mean velocity of flow in meter per second or feet per second. P is equals to mass density of fluid in kilogram per cubic meter or slugs per cubic feet. Y is equals to unit weight of fluid in Newton per cubic meter or pound per cubic foot. A simple problem using steady flow of a fluid stream. Question number 1. The discharge of air through a 600 mm pipe is 4 cubic meter per second. Compute the mean velocity in meter per second. Solution. We will use Q is equals to VA. Then we will substitute only. This is 4 is equals to V multiplied by 14 pi times 0.62. Then V is equals to 14.15 meter per second. Here is another example. A pipeline consists of successive lengths of 380 mm, 300 mm, and 250 mm pipe with a continuous flow through the line of 250 liter per second of water. Compute the mean velocity in each size of pipe. First, we will write down the formula, which is Q1 is equals to Q2 is equals to Q3 is equals to Q. V1A1 is equals to V2A2 is equals to V3A3 is equals to Q. Then substitute. V1 is equals to V2 is equals to V3 is equals to 4 multiplied by 0.25 pi multiplied by 0.3802. The first answer will be 2.20 meter per second. V2 is equals to 4 multiplied by 0.25 pi multiplied by 0.3002. We will be getting 3.54 meter per second. V3 is equals to 4 multiplied by 0.25 pi multiplied by 0.2502. This will be 5.09 meter per seconds. Okay, for our last topic, we will talk about propulsion of variable mass. In mechanics, a variable mass system is a collection of matter whose mass varies with time. So it means that mass is directly proportional to time. It can be confusing to try apply Newton's second law of motion directly to such a system. Instead, the time dependence of the mass m can be calculated by rearranging Newton's second law and adding a term to account for the momentum carried by mass entering or leaving the system. The general equation of variable mass motion is written as Fext plus Vrel multiplied by dm over dt is equals to mdv over dt. This means that the mass is directly proportional with time, or mass is with respect to time, where Fext is the net external force on the body, Vrel is the relative velocity of the escaping or incoming mass with respect to the center mass of the body, and V is the velocity of the body. Here's a simple problem. A spacecraft is moving in gravity-free space along a straight path. When its pilot decides to accelerate forward, he turns on the thrusters and burn fuel is ejected at a constant rate of 2 times 10 raised to 2 kg per second at a speed of 2.5 times 10 raised to 2 meter per second. The initial mass of the spacecraft and its unburned fuel is 2.0 times 10 raised to 4 kg, and the thrusters are on the 30 seconds. Okay, this is the question for letter A. What is the thrust or the force applied to the rocket by the ejected fuel on the aircraft? Letter B. What is the spacecraft's acceleration as a function of time? Let will be the momentum of the ejected fuel will be P is equals to mgv. The ejection velocity V is equals to 2.5 times 10 raised to 2 meter per second is constant, and therefore the force is F is equals to dp over dt, and it is equal to V times dmg over dt, or it is equal to negative V multiplied by dm over dt. Now dmg over dt is the rate of change of the mass of the fuel. The problem states that 2.0 times 10 raised to 2 kg per second is substituted on the formula of F is equals to V times dmg over dt. Then 2.5 times 10 raised to 2 meter per second times 2.0 times 10 raised to 2 kg per second. The answer is 5 times 10 raised to 4 newtons, and that's the answer for letter A. For letter B, we define M to be the combined mass of the empty rocket plus however much unburned fuel it. This is contained by M is equals to mr plus mg. Then we will use the Newton's second law, which is A is equals to F over M. Then we derive F over M is equals to F over mr plus mg. The force is constant and the empty rocket mass mr is constant, but the fuel mass mg is decreasing at uniform rate because the mass is varies to time. Mg is equals to mg times t is equals to mg initial minus dmg over dt times t. Then this gives us at is equals to f over mgi minus dmg over dt times t. At is equals to 5 times 10 raised to 4 newtons all over 2.0 times 10 raised to 4 kilograms minus 2.0 times 10 raised to 2 kilogram per second multiplied by t. Then you need to use the function we obtained in part B and just substitute the numbers given to get the continuously decreasing fuel in the rocket, and that's the answer for letter B. And that's the end of our video. Thank you for listening.